Welcome to our comprehensive module on Cloud SQL integration. This module focuses on integrating applications with databases using Google Cloud SQL and exploring alternative database solutions. Cloud SQL integration involves establishing secure, efficient connections between your applications and Google Cloud SQL database instances. This integration is fundamental to building scalable, reliable cloud-based applications. When integrating with Cloud SQL, developers face several critical challenges. These include managing database connections efficiently, handling scaling requirements as applications grow, ensuring high availability for mission-critical systems, and managing concurrent database access. To address these challenges, we will explore proven solutions including Cloud SQL Auth proxy and direct connection methods, connection pooling strategies for optimal performance, and alternative database solutions like Firestore for specific use cases. Throughout this module, you will learn about various connection methods and authentication approaches, connection pooling techniques for performance optimization, strategies for handling concurrency and scaling, implementing high availability solutions, exploring alternative database options, and applying real-world best practices for production environments. By the end of this module, you will have a comprehensive understanding of Cloud SQL integration patterns, performance optimization techniques, and the knowledge to implement robust database solutions in your cloud applications. When connecting applications to Cloud SQL instances, there are two primary methods available. Each method offers distinct advantages for different architectural requirements and security considerations. The Cloud SQL Auth proxy serves as an intermediary that creates secure connections between your application and Cloud SQL instances. It automatically manages short-lived SSL certificates and handles IAM authentication. The Auth proxy provides automatic SSL certificate management, IAM-based authentication, and requires no direct network configuration. This makes it an excellent choice for applications that need secure, managed connectivity. Now let's examine the second method, direct connection through private service access. Private service access enables direct connections between VPC resources and private Cloud SQL instances through VPC peering. This approach keeps all traffic within Google's managed virtual network infrastructure. Direct connections via PSA offer several advantages. Traffic remains within the managed virtual network, providing lower latency for VPC-based applications, and can support up to 50 Cloud SQL instances per 24 CR range. Let's now compare these two connection methods to understand when to use each approach. This comparison highlights the key differences between the two connection methods. The Auth proxy offers simplicity and strong security for external applications, while direct PSA connections provide lower latency and are optimized for VPC-based applications. When selecting a connection method, choose the Auth proxy for simplicity and external application access, or private service access for VPC integration and optimal performance within Google Cloud's network infrastructure. Connection pooling is a fundamental technique for optimizing database performance in cloud applications. Understanding how it works is essential for building scalable systems. A connection pool is essentially a cache of database connections that are shared and reused across multiple applications or requests. Instead of creating new connections each time, applications draw from this pre-established pool. Without connection pooling, each application request creates a new database connection. This approach leads to significant overhead, as establishing connections requires authentication, network handshakes, and resource allocation. Each request creates multiple new connections, leading to resource waste, increased latency, and potential database overload during traffic spikes. With connection pooling, a dedicated pool maintains a cache of pre-established database connections. Applications request connections from this pool rather than creating new ones. Applications connect to the pool using lightweight requests, while the pool maintains a smaller number of persistent connections to the database. This dramatically reduces connection overhead. Connection pooling provides several critical benefits: reduced connection latency by reusing existing connections, optimized resource utilization through connection sharing, better handling of sudden traffic spikes, and overall improved database performance. Google Cloud offers managed connection pooling specifically for Cloud SQL PostgreSQL instances. This service automatically absorbs sudden connection spikes, dynamically reuses existing database connections, and optimizes performance, especially for applications with scaled connection requirements. The performance impact of connection pooling is substantial. Applications without pooling experience significantly higher connection latency, while those using connection pooling achieve much faster response times and better resource efficiency. Connection pooling is a critical optimization technique that caches and reuses database connections, significantly reducing latency and improving resource utilization. Google Cloud's managed connection pooling for PostgreSQL provides automated optimization, making it essential for applications that need to handle traffic spikes efficiently. Concurrency challenges arise when multiple applications or users attempt to access the database simultaneously. Without proper management, this can lead to performance degradation and system overload. CloudRun imposes a specific limitation. Container instances are restricted to 100 connections per Cloud SQL database when using the built-in Cloud SQL connection. This constraint can become a significant bottleneck in high-traffic applications. To mitigate concurrency challenges, implement two key strategies. First, limit concurrency using the max instances configuration parameter. This prevents excessive container scaling that could overwhelm the database. Second, implement connection pooling to efficiently manage database connections. Connection pooling reuses existing connections rather than creating new ones for each request, significantly reducing the connection overhead. Monitoring with cloud monitoring is crucial for identifying and resolving performance bottlenecks. Establish alerts for connection count, response time, and error rates to proactively address concurrency issues before they impact users. High availability, or HA, is a critical feature that reduces downtime when a zone or instance becomes unavailable. Understanding how Cloud SQL implements HA is essential for building resilient database systems. High availability in Cloud SQL serves three primary purposes. It reduces downtime when zones or instances fail, provides automatic failover capabilities, and ensures business continuity for critical applications. A Cloud SQL instance configured for high availability is called a regional instance. It consists of a primary zone containing the primary instance and a secondary zone containing the standby instance, both within the same Google Cloud region. The primary and standby instances are connected through synchronous replication, ensuring that all data changes are immediately replicated to the standby instance before confirming the transaction. During normal operation, applications connect to the primary instance, which handles all read and write operations. The standby instance remains synchronized but does not serve traffic. When the primary instance fails due to zone outage or hardware issues, Cloud SQL automatically detects the failure and initiates the failover process. The standby instance is automatically promoted to become the new primary instance. Applications are redirected to the new primary, typically within 60 to 120 seconds, minimizing downtime. Cloud SQL provides high availability through four key mechanisms: automatic failover for rapid recovery, synchronous replication for data consistency, automated backups for data protection, and self-healing mechanisms for proactive issue resolution. High availability in Cloud SQL delivers significant benefits. It minimizes downtime during failures, provides automatic recovery without manual intervention, ensures data consistency through synchronous replication, and supports critical business continuity requirements. Cloud SQL provides two primary scaling approaches to handle increasing workloads and traffic demands. Understanding these scaling strategies is essential for building robust database architectures. Vertical scaling involves resizing your Cloud SQL instance by increasing its computational resources. This means adding more CPU cores, memory, and storage capacity to a single database instance. When you vertically scale your instance, you upgrade to more powerful hardware specifications. This approach is straightforward, but has limitations as you can only scale up to the maximum instance size available. Horizontal scaling takes a different approach by distributing the workload across multiple database instances. This is achieved through read replicas, which are copies of your primary database that handle read-only operations. Read replicas are automatically synchronized with the primary instance, receiving all data changes through continuous replication. This allows you to distribute read queries across multiple instances while maintaining data consistency. A fundamental best practice in database architecture is separating read and write workloads. This separation allows you to optimize each type of operation independently and prevents read-heavy queries from impacting write performance. Write operations such as inserts, updates, and deletes are directed to the primary instance, while read operations like select queries are distributed across read replicas. This distribution significantly improves overall system performance. The optimal architecture combines high availability configuration with multiple read replicas. This approach provides both fault tolerance through automatic failover and enhanced performance through distributed read operations. This architecture delivers automatic failover protection, distributed read performance, geographic load distribution, and reduced latency for users. Implementing Cloud SQL read replicas alongside high availability represents the best practice approach for handling increased traffic while maintaining system reliability. While Cloud SQL provides robust relational database capabilities, Google Cloud offers alternative database solutions that may better suit specific application requirements. Firestore represents a fundamentally different approach to data storage and management. The fundamental difference lies in data structure. Cloud SQL organizes data in structured tables with predefined schemas, while Firestore stores data as flexible documents that can contain nested objects and arrays. Firestore operates as a serverless database, eliminating the need for server provisioning and management. Unlike traditional databases that require capacity planning, Firestore automatically scales resources based on application demand. Firestore provides strong consistency guarantees, ensuring that all clients immediately see the most recent data changes. This eliminates the eventual consistency challenges often associated with distributed databases. Firestore excels in specific application scenarios. E-commerce platforms benefit from flexible product catalogs and user profiles. Gaming applications leverage real-time capabilities for leaderboards and multiplayer features. IoT systems utilize Firestore for sensor data collection and device management. Real-time dashboards take advantage of live data synchronization capabilities. When choosing between Cloud SQL and Firestore, consider your application requirements. Cloud SQL suits applications requiring complex relational queries and structured data. Firestore excels for real-time applications, rapid prototyping, and scenarios requiring automatic scaling with minimal operational overhead. Database bottlenecks are common challenges in production environments. Understanding how to identify, resolve, and prevent these issues is crucial for maintaining optimal application performance. In cloud-run environments, multiple container instances can simultaneously attempt to connect to your Cloud SQL database, creating connection bottlenecks and overwhelming the database with concurrent requests. The first solution is implementing proper concurrency management. By setting max instances limits in CloudRun, you control how many container instances can run simultaneously, preventing database overload. Connection pooling is essential for efficient database resource utilization. Instead of each application creating direct connections, a pool manages and reuses database connections, significantly reducing connection overhead. Continuous monitoring is crucial for identifying bottlenecks before they impact users. Cloud monitoring provides real-time insights into CPU usage, connection counts, memory utilization, and can trigger alerts when thresholds are exceeded. Cloud SQL provides numerous automated features that reduce operational overhead and ensure reliability. These include automated daily backups with point-in-time recovery, automatic replication for high availability, seamless patch management, and a guaranteed 99.95% availability service level agreement. By implementing these best practices, connection pooling, concurrency management, continuous monitoring, read replica distribution, automated backups, and leveraging Cloud SQL's managed features, you can ensure a scalable, reliable, and efficient database integration for your applications.